just by using the Haar measure. So write the product over the links of pH link, the function f1, and one of a and here f2. Because there is this measure, so this is on SU2, yeah. Because this object exists on the group SU2, there is this measure, we can perform this integral, we can compute this. So because we have this integral, this gives us the natural notion of an inner product in this space of symmetrical functions. So here I have wrote it with the same graph, but two different functions. You could also ask me like what happens if the two graphs are different. If the two graphs are different, there is this has to be modified slightly. There is a natural way to also write this down. So it's not useful at all for what we're going to do. But don't be bothered by the fact that the graphs are the same. This works for any graphs. If you take one state, define on one graph and one function, another state, define another graph, another function, this would still be this would still hold. And in fact, then, what you can do is to just extend. So now with this inner product, we obtain a Hilbert space. And now this Hilbert space, so this turns gamma into a Hilbert space, H gamma. This is a Hilbert space, but just on one graph, gamma. But now the full Hilbert space, now the full kinematical Hilbert space that we're going to start with is just given by the sum over all the graphs embedded in the manifold of these graph Hilbert spaces. So whenever I have one graph, I have a Hilbert space structure which is given by this. So the functionals are given by this, and the inner product is given by this. And for each of these graphs, I can take this sum over all the graphs in the manifold and get what people call this kinematical Hilbert space. And then there is a very beautiful result by by Ashtekar and Lewandowski that have been able to show that then this continuum Hilbert space, once we sum over all the possible graphs, is an L2 space over what we call the generalized connections. So not really these connections, but a bit extended definition. So L2 over the space of connection A and a certain measure, which is the Ashtekar Lewandowski just a certain measure. So this means that if you want, this is just to say that there is a contact with the. You don't have to be troubled by the fact that we define the structure on the graph. This graph that we choose in the beginning was just like a structure by hand to write down one state and one Hilbert space and see what the structure is. But then we can sum over all these graphs, so get rid of this dependency on the graphs, sum over all the graphs, and this is the full kinematical Hilbert space. So it's an L2 space, and over, so this A in fact is the space, I'll write it like this, so round like this. This is an extension of the space of smooth connections on the manifold. It's an extension because it allows also for distributional connections. So this is just a technical thing, it's not useful for us, but in this construction, once we do this, what we end up with is the L2 space not over the original classical configuration space, but over a larger space. And this is what happens usually in any quantum field theory. In any infinite dimensional quantum theory, the quantum configuration space is usually larger, it's bigger than the classical configuration space. You have to consider distributional objects and more extended and more general than the mathematical point of view objects. So here the same thing happens. We see that the L2 space is over connections, but a bit more general than the usual classical smooth connection. But it's not important. Yeah, so now that we have this, now we can ask the question of what is the convenient basis in this Hilbert space? What is the convenient choice of basis? And the convenient choice of basis, to find it, we're going to use this, this Peter-Val theorem that enables us to write down functions over SU2. So this theorem tells us, so the theorem tells us that so a function over the group SU2, this is a function, its argument is an element of the group SU2. This can be written as a sum over spins of certain coefficients, so j and n, and j. But these are the usual Wigner representation matrices. So I have an SU2 space, so with we choose J and like this as a ket. And then this is just given by the these are the usual representation matrices in the representation indexed by the spin J. So in SU2, I have all these representations indexed by one half integer spin. And the Peter-Val theorem tells us that the way to write any function on SU2 is on the basis of these unitary irreducible representations of SU2. So there are certain coefficients, and the basis is given by this. So this is the representation. Since we have 5 minutes, maybe I will skip some things. Okay, so now this we can extend this to any generic function, because this is a function of only one argument, but the states that we wrote before. So now I take any state like this, and so this by the same thing can be written as a sum over all the spins. So J1, J2, Jn. Certain coefficients, so J1, Jn, and 1, n is 1, n, so a certain like coefficient, and then the product of the representation matrices for all the this is just saying that instead of so because we started classically with the connection, which is valued in the Lie algebra, then we took the exponential, which is valued in the group, and then because on the group we have these mathematical structures that enable us to write any function on the group in this basis of unitary irreducible representation. This is a convenient way to write down a basis for these quantum states. And you see that this is the reason, in fact, and you can understand, for maybe you heard this object, so this is why in quantum gravity, these states of the gravitational field, we call them a spin network states. Because it means that we have a state of the kinematical, so you have a spatial slice here, the spatial slice sigma, and an initial configuration, so space of the gravitational field on this slice is just given by giving me an arbitrary, so a spin network state. It means that there is a state here, so it's a graph, and the links are labeled now by this representation. You see that the link 1 is labeled by the spin J1. The link 2 is labeled by the spin J2. So in fact, if you know, because this is the basis of the space, if you know just the spins labeling the links, you know the information about this, in fact, through this formula. So we have here spin J1, J2, J3, J4, J6. This is a network of spins, so a spin network. So in this sense, the spin networks are the kinematical states of the gravitational field. Now you change this spin to another spin, J6 or J8.
But spin of what? Spin of what?
Now SU2 spins, so yeah. So these spins are not spins of any It's just a mathematical coincidence that these spins are the same as the angular momentum or the SU2. These are not the spins of any particles or any physical thing. It's just a way to write down the objects, a convenient way to index what the states are.
For instance, you still only have geometry.
Yeah, this is just pure gravity, so no matter, this is pure geometry, pure gravity. But because the connection, because classically the Hamiltonian formulation was in terms of the group SU2, and in the quantum theory you can use the structure on SU2 to write the Hilbert space in this way. And once we do this, all we have to know about is the spins. So this is why only the spins remain here. So it's just gravity for the moment. It's pure gravity, it has no matter, it has no... This is vacuum gravity.
But still gravity without gravity. It's not spin to field.
Yeah, for the moment, of course. For the moment, there are no gravitons, or it's hidden somewhere. It's hidden somewhere.
Has it something to do with the spin forms?
Yeah, so the spin foams, now this is a spin network because it's just a network, but now the spin foams are the dynamics of this in fact. Now it's just, this is why we call this kinematical, because for the moment this doesn't know anything about the dynamics. This is just now, as usual in quantum theory, we have to write down the states. So what is the state? Once we know what the states are, so how to write the state of the gravitational field, then you have to ask, okay, now how the constraints, so the Dirac constraints, are acting on the states. So now on these states I have to impose the Gauss constraint. This will give us the gauge invariant space, then the diffeomorphism constraint, and then the dynamics, the Hamiltonian constraint. And once we impose the dynamics, these spin networks, they're going to evolve in time. They're going to evolve and give, so if you imagine that this network is evolving in time, it will give you a foam labeled by spins. So this is the spin foam. This is why the spin foam is the dynamics, the covariant picture of this kinematical. This is just for the moment the kinematical strength.
This graph is like a picture or path in the phase space.
If you will, yeah. If you give me such a graph, you give me a state of gravity. So in some sense, this is what happens in loop quantum gravity. What we try to do is always to define a very abstract object, which is the path integral, or rather this. Try to compute the product between G1 or some physical inner product, and you write this as the sum over metrics, e to the I and the action. Action. This is the Feynman path integral of gravity between two in and out states. This is completely ill-defined. There is no clear meaning to this, but in some sense, heuristically if you want, what happens here is that in loop quantum gravity, we know we have a control over these states. So over the in and out states. We know that the state of the gravitational field, we have to specify these states. To specify such a state, we have to specify a graph like this. Certain values of the connection along certain links. Now you see that if you have here the final state, which is a certain graph like this, and an initial state here, so this is a sigma 2, this is sigma 1, so this is at time minus infinity plus infinity, then the question is what is the dynamics? How do I evolve from this state to this state? And this is the amplitude for this. This would be a quantum gravitational process. So in the middle here, I create an atom of space-time. I create an atom of the gravitational field. And the reason is that here I have a certain configuration of the gravitational field. So the metric is G1 on the hybrid surface sigma 1. And here I have a final configuration. So how do I go between the two? What is the amplitude for this process? So for example, I can imagine that this evolves, and here I have a node that is created. Goes from here, here, here. So you have to see this in space. Now this is like a 3-dimensional picture. So this is the time evolution. And so the role of the game, in fact, the final goal is to specify what is the amplitude for this. So there is a Feynman amplitude, in fact, associated to this process. And this amplitude you can see as, yeah, it's just like a Feynman amplitude, in fact, for this given process. But for the moment, what we are doing now is just to describe the kinematical states. So we're forgetting about the dynamics, what happens here, what are the states. So I'll start with the classical Poisson algebra. So gravity as a Yang-Mills theory. So gravity in terms of the connection and the conjugate momentum. how do I write these objects in a quantum theory? How do I turn these into quantum operators? And how do I find a Hilbert space structure? So the only way here to get a Hilbert space structure is to go through these holonomies and then use the structures on the group SU2. And so, yeah, so just for the interpretation, so that on Friday we can do quantum cosmology. What is important in quantum cosmology is two things imported from this. So the idea is that, okay, we take this construction, this idea, what happens if we apply it to cosmology? So the first thing to do, the first lesson is that to do the quantum theory, you have to work with holonomies. So not with the connection, but with exponentials of the connection. So in cosmology, we are going to do the same thing. This is the first step. And the second step, so we didn't have time to derive it here, but I can tell you what happens is that now we understand that now we have a quantum theory, and so the fluxes that we introduced earlier, they act on this Hilbert space, in fact. And the way they act is by derivative with respect to the connection. Now what you can do, remember that classically these come from the electric field. So EI over surface. And so this is in fact, this is encoding the metric in fact. This E field is really encoding the spatial metric. So with the spatial metric, classically, I can construct operators. I can construct, for example, the operator that measures the surface of the area of a certain surface. So you give me a surface here, with certain coordinates on the surface. I can construct classically, measure the area of this surface given the metric. So now, because in this framework we have quantum geometry, because this E field becomes a quantum operator, we can construct a quantum area operator, in fact. So we can just take the classical expression for the area operator, turn it into a quantum operator, and then act on these spin-network states. Because these are our kinematic states, and see what happens. And the result is that we find that the area of this surface is discrete, in fact. And we can already now heuristically understand why it's discrete. It's because the underlying group is SU2, in fact. So because it's SU2, it's observable. This area is going to be given by the Casimir of SU2, and the Casimir of SU2 is a square root of j plus 1. So it's discrete, because it's labeled by the spins j, which are discrete. But this was the first historical result of group quantum gravity, is that once we have this kinematic constructor, we can look for the length operators. So how do I measure the length of a curve, the area operator, and the volume operator? And all these operators are discrete. They have a discrete spectrum. And in fact, the last comment is that what this graph encodes, in fact, this is completely dual to a discretized manifold in this sense. So what happens is that imagine that you have a surface intersecting this link here. I can construct a quantum operator measuring the area of this surface. And what you will get is that this surface is in fact proportional to square root j plus 1 with 8 pi length squared. This is what we will obtain. So maybe on Friday. Let's given by this. And what we also obtain is that there is a volume operator, and for the volume operator, what is important is what happens at these nodes here. So the picture, if you want, is that for every node, they have a tetrahedron, if you want, a chunk of space, and for each link, they have a surface. So it's exactly as if here, so you give me a manifold M, a full manifold M. Or rather a spatial slice, sorry. Let's take a spatial slice sigma, which is three-dimensional. Now I say no. Now I don't want to work with sigma, I want to discretize sigma. I want to work with instead of having sigma, I will glue tetrahedron together like this. One here, one here, for example. So what we have just seen, in fact, so not completely, but anticipate the result, is that in loop quantum gravity, this is really what happens. If I look very closely at the geometry of this spatial slice, I see a discrete structure. I see that, so these tetrahedron are going to be dual to these nodes, in fact. So the graph here, and the links. So this is what this graph means, in fact. Why is this graph a state of quantum geometry? Because this graph is a geometry of a manifold, if you want. This graph, so you can imagine that dual to each link, I have a certain phase, and dual to each node, I have a certain volume, a certain region. So here I have like a three-dimensional bubble like this. And the link is piercing the surface of this bubble, if you want. And so for loop quantum cosmology, what will be important is this discreteness. So because what is very important is that this area spectrum has a non-vanishing minimal eigenvalue, in fact. So it cannot go to zero. So the area never goes to zero, in fact. So this is really the entire spirit of this approach, is that we derive from the canonical quantization the fact that there are no degrees of freedom living under a certain minimal band, in fact. And this is really nice and sort of compatible with the philosophy that we mentioned in the beginning, which is that if gravity is a field, but gravity is geometry, and if this field is quantized, we have a notion of quantum geometry. And this is in fact the quantum Riemannian geometry that we see here. You see that if you measure the area of a surface, if you have like a measuring device very accurate, you will see that the area of the surface will be discrete. So because it is discrete, you will have very important consequences in cosmology.
So let's stop here today. Do you have any questions? Okay, so let's thank the lecturer.